Hello, everyone. In this lecture, I would like to talk about registers, shift registers, and counters, which is chapter 6 in our textbook. Now, in chapter 5, we have seen how we can store one bit of information in flip-flop. So D-type flip-flop was a typical example of a cell that we can write one bit of information into it. And this is actually known as a cell, memory cell, which stores one bit. Now, if we combine these cells, let's say I can have a 4-bit of that, okay, and I'm storing, let's say, 0, 1, 1, 0. This is a collection of cells or a collection of flip-flops that we can have a common clock, common enable, and the common load, asynchronous or synchronous set or reset. Now, this is called a register. So it's a collection of flip-flops with a common input signals or the control signals, let's say, asynchronous or synchronous, and we can implement a register with 4 bits, 8 bits, depending on the architecture, 16 bits or 32 bits. Now, what is this? Is actually, we can form it like flip-flop 1, 2, 3, and 4 of those. And all of those are D-type flip-flops, let's say. Okay, and each of those has their own inputs, common clock. Okay, so clock, you might have an asynchronous set and reset over there, but this is how it looks like. Now, in order to implement, let's say, a parallel load capability, now what will happen with the parallel load? We have to have some kind of a load or enable signal that we can activate that, so at the same time the data will be loaded down into each of these flip-flops. So how can we do that? We can do that by using a multiplexer. So simple multiplexer, 2-to-1 multiplexer, will actually going to work for the requirement that we need to have. So when we have got, let's say, 0 and 1, when it is 0, it's going to come from the Q out. Okay, it's like a feedback. Okay, and when it is 1, it's coming from outside, let's say the 3 for that. And the select is the enable. Okay, so enable signal will activate that. And this can be repeated for the others. So 0 and 1, this is going to be D2. Then the select of what that enable is going to be shared. And then another one. So 0 and 1. And then enable D1. And also the Q. This is Q prime, and Q. And then the last one. So 1 and 0. Again, enable D0. And this fits into Q and Q bar. Okay, so if you want to have a parallel load, you just need to enable the multiplexer so it will load a new data from D3, D2, D1, and D0, and that will be loaded down into the flip-flops. So we can say that as a table enable, and Q next. So when enable is 0, this is actually going to hold the previous data, okay? And when it is 1, it's going to have the data in. And this can be represented with a symbol with data input, with enable input, and of course the clock. And we have got Q and Q prime. And this will represent our parallel load D-type register or D-type flip-flops. I hope it is clear. By the way, if you have any questions, please note them down. And while we are having the live sessions, you can ask me those questions. So 4-bit register with parallel load is demonstrated, and it's actually a single bit over here, but that can be represented as 4-bit with 4 D-type flip-flops as shown over here. So we can just use a symbol if you want to implement a 4-bit one after the other, and we can just put that down. Okay, so if we continue from the slides, registers, as we already said, collection of flip-flops. So parallel load capability, by using an enable, we can easily implement a parallel load capability. So this is what is demonstrated. And if you want to have it a 4-bit or 8-bit or 16-bit of that, we can just use that symbol, and we just need to duplicate it and connect all the inputs and outputs accordingly. So slide 7 shows that. So this is a parallel load register with 4 bits. So D3 to D0 represents inputs. Enable is the load. So when the load is activated, new data will be loaded. Otherwise, it will hold the previous data. And Q is represented 3 down to 0. And that's the symbol for it. Now, we can also add a active low clear or maybe a reset. So it's like an asynchronous. Whenever we press the reset, it will reset the outputs so that we can have an asynchronous operation. Now, this is now I want to talk about something that is again a job interview question. What's the difference between little endian and big endian? So little endian, because when we are talking about registers, this is important. Big endian. Maybe I have to change the color. So big endian. Now, little endian means ending with little, actually. So let's say I have got a 4-bit register. Okay. Now with little endian, bit 0 is over here. Okay. And bit 3 is on the left-hand side. So this is most significant bit. This is less significant bit. And then we have got bit 2, bit 1, and so on. In big endian, so as it says, the big one is on the ending side. So that means it's on the right-hand side. So this is going to be LSB to MSB. And that will be bit 0, bit 1, bit 2, and bit 3. Okay, and this is known as big endian. Now, when we are talking about these registers, when we put them down or physically connecting them, we have to state what type of register we are having. Big endian, little endian, and that's totally coming from here. Okay, so D0 down to 0 up to 3. So it's going to be a little endian. sorry, big endian. If it is 3 down to 0, it means little endian. Okay, so MSB, which is bit 3, is on the left-hand side or is at the bottom or maybe top. So you have to arrange that accordingly so that you can have a little endian or big endian. Okay, so here's an example of a big endian format. So as you can see, the most significant bit is on the right-hand side. So this is big endian notation. Okay? And normally, in most of our examples, we are going to use little endian. So most significant bit on the left-hand side. Okay, so if we carry on, 4-bit register with active low clear, as I already mentioned, you can add a asynchronous set or reset to the registers, like we have done with the flip-flops. So active low clear will clear the registers whenever we pressed asynchronously. It's not working with the clock, and it can easily be demonstrated by adding a reset or clear input. Now, 4-bit register with parallel load, it's actually, as I already demonstrated over here, it's just a simple multiplexer. So either we select a new one or we hold the previous value. So this 2-to-1 multiplexer can be seen as a 2 AND gates and NOR gates. If you do remember from chapter 4, in order to implement the multiplexer, we use 2 AND gates and OR gates. So function f is equals s prime a or s b. This was the equation for 2-to-1 max. So if you want, you can just use a multiplexer symbol in front of the D-type flip-flop, or you can use the AND gates and the OR gates to represent the logic required. So 0, 1, this is going in, this is data, and that's the clock. Let's put the clock down because we need a select line. And this is the enable or load, let's say. Okay, so this is actually one of those, is actually representing one of those. It's the same thing. Okay, and when the load is 1, it activates the multiplexer and we load the new data in. Now this is a 4-bit register with parallel load. Now there are different types of applications that we use flip-flops in order to design a registers or maybe a shift register, which is another one of the most used device in logic design. Now 4-bit shift register, for example, if you want to demonstrate this, we need flip-flops, 4 of those again. Okay, so 4-bit shift register. Now, 4-bit shift register is nothing but a D-type flip-flops. D, Q, oops. Q bar, D, Q, Q bar. The clock is common again. Now, shift register, as it suggests, is shifting the values from one end to the other. So this is actually directly connected. The output of one is connected to the output of the other one. And this one is known as serial out. I'm writing over here. And this is known as serial in. SI, S out, serial in, serial out. Now, and this is the clock. If you want, you can have some parallel outputs, which we can add it from here, like Q3, Q2, Q1. and the other one is just Q0 or S0, which gives us the serial output. Now, what do we mean by serial in, serial out? We can demonstrate that. Now, we can have a simple demonstration using the clock, as well as this is a clocked circuitry. So we have got clock serial in data, Q3, Q2, Q1, and Q0, which is serial out. Now, how are we going to use this? At clock 0, okay, serial in, let's say we have got a number. Let's say serial in is 1, okay? Now, we are at the beginning, nothing is working at the moment, so that means all of the flip-flop outputs are going to be 0, 0, 0, and 0. So we are just over here now. We haven't done any operations yet at clock phase 0. Now, at clock phase 1, on the first cycle of the clock, let's say I'm inputting another 1, but this one that I have got in SI will be shifted over here. So that means this is going to be 1, okay? And that 0 will be shifted here, and that 0 will be shifted to the right, and that 0 will be shifted to the right. So in the first, we are having an output. So I'll say SI was 1, okay? Then another one is coming in. So this is shifted, Q3, Q2, Q1, and S0, Q0. Now, on the third cycle, or clock cycle 2, I'm inputting another 1, but the previous one is also feeding in to the next one. So this is going to be 1, and this one will be fed over here. That will be 1, and this will be 0, and this will be 0. So I have just got 2 1s in the flip-flops now. So 1, 1, 0, 0 will be the outputs. Then I can repeat that. I can add another cycle and with another 1, for example. Now the previous one will be shifted on the clock so that the new data can come in. And that one will be shifted, and that one will be shifted, and that 0 will be at the output. Okay? And if I repeat cycle 4, this is going to be, let's change it to 0. Now this one is actually transferred. So this will be 1, this will be 1, this will be 1, and this will be 1. Now all of them are 1s. Now we started with 0, 0, 0, and now we have got 1, 1, 1. So 4 cycles that we have got, and the outputs are all 1s. Now, if we carry on, if I add another cycle with 0, now this will going to be 0, okay? This will be 1, this will be 1, this will be 1. And cycle 6, I can have 1. I'm just putting a random numbers. Okay, these are all just random numbers for SI. Then this will be 0, and that 0 will be shifted, that 1, and that 1. Now I have got 0, 0, 1, 1. And last one, cycle 7, another random input, so I'll put 0 for that. So my 1 will be shifted, and the rest is going to be shifted accordingly. So 0, so 0, and 1, and that the last one will be shifted out. So I have got 1001, which is 9. And this is a typical shift register operation where we are just shifting from one flip-flop to the other based on the rising edge or the falling edge of the clock. And the symbol for it, we can draw also the symbol. So the symbol for it is we have got serial in, the clock, serial out, and that's it. Okay, so this is input, this is output, just to represent it. This is known as shift register. You can have 8-bit, 16-bit, 32-bit, depending on the architecture that you are using. We can implement a shift register. And this is also demonstrated in the slide. I hope it is clear. And we can also use shift registers to implement a universal shift register. What do we mean by universal shift register? Now, rather than just having shifting from one side to the other, we can have multiple operations with universal shift register. So these operations can be defined by the designer or maybe in the specifications. So I'll say we have got operations like when S is 1, S2, S0, S1. Okay, so 0, 0, 0, 1. These are the mode controllers. So what kind of operations are we going to do? They are based on these S1 and S0. And the register operation, now 0, 0, let's have it hold, so no change. 0, 1, let's shift right. 1, 0, shift left. And 1, 1, do parallel load. So we can do parallel load as well. Now, we have got 4 different operations that we can implement with universal shift register. So what do we need to use here? Think about it. As we are having a most of operations with 2 controllers over there, mode controllers, we can actually use a multiplexer. So 4-to-1 multiplexer with a D-type flip-flop will actually solve our problem. So let's say I'll have 4-to-1 multiplexers, 4 of those. I hope I can fit everything here. And the outputs are going to be connected to the inputs of the flip-flops. Okay, D inputs, and we have got clocks connected Q, Q bar, Q, Q bar, Q, Q bar, Q, and Q bar. And modes of operations 0, 0, 0, 1, 1, 0. I know my pen is too thick, so that's how I can fit everything. Okay, so I'm actually feeding S0, S1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, and 0, 0, 0, 1, 1, 0, 1, 1. Okay, so we can implement universal shift register. The clocks are all connected. So we can have all connected here, which represents the clock. Maybe I can shift that a little bit down. Okay, so how are we going to use these operations? Now, S00 is no change. That means, I'll use a different color. When it is 00, we are actually feeding back the previous values. Okay, so feeding back each of those previous values. Halt for the flip-flop. Now, when it is shift right and shift left, we are just going to have it from one output to the other. Now, I'll say this is Q3, this is Q2, this is Q1, and this is Q0. Okay, so this is working in 3 down to 0. Right, so shift left and shift right. Shift left means we are actually, maybe I can demonstrate that here somewhere. Shift left Okay, so 3, 2, 1, 0, 3, 2, 1, 0. When we are shifting left, we are actually shifting from least significant bit to the most significant bit, shifting to the left. Okay, least significant bit to the most significant bit. So if we give an example, like for example, I have got 0, 1, 1, 0. Now, if you want to shift that, that 0 comes over here, that one comes over here, that one comes over here. And that 0 disappears. Now, over here, we have to fit in a new value. And in a shift register, this is always 0. Okay? So we fit in zeros. So this is going to be 0. Okay? And the 0, the most significant bit, it will disappear. So in order to do that, now bit 0 is going to be connected to bit 1. Bit 1 will be connected to bit 2, bit 2 to bit 3. Okay? So I can say that when it is 0, 1, which is shift left, Q0 is going to be fed into Q1. So I'll say Q0 over here. Then Q1 will be fed into Q2. And Q2 will be fed into flip-flop 3. So this is actually shifting. Now Q0, it's going to fed in a serial input, let's say, SI, shift left. Okay, so generally this is 0 for SI. Now we have completed no change and shift right. The next thing to do, shift left. Now shift left is operation in other way round, which I can demonstrate here. Now shift left 3, 2, 1, 0, 3, 2, 1, 0. Sorry, I've done it other way around. Okay, hang on. This one, shift right. So the first one was shift right, but we have done shift left. So we have to change those down. Sorry. This was shift right, left. So this was actually 1, 0, not 0, 1. Okay. So I'm just repeating that. So as we are doing shift left, 1, 0, we are going to fit these into 1, 0. So 0 will be fed into Q0 will be fed here, Q1, and Q2. Okay, because shift left is 1, 0. And then this one is serial in, shift left. This is 0, 1 as well. And the shift right, which I accidentally skipped, is shifting from 3 to down to 0. So if I have 0, 1, 1, 0 again, then bit 3 will be shifted to bit 2, bit 2 will be shifted to bit 1, bit 1 will be shifted to bit 0, and the bit 0 will just shift out, and over here we will have another serial in. So that means Q3 will be fed in over here to Q2, and then Q2 will be fed down over here, and Q1 will be fed down from here to Q0, and Q3 will have another serial in for this operation, shift right. Okay, and this will be the shift right. Now, when it says parallel load, like we have done in the previous example, we just need to load parallel data. So D3, D2, D1, D0. So 0, 0, no change. Okay. 0, 1, shift right, shifting right. 3 goes to 2, 2 goes to 1, 1 goes to 0. 3 goes to 2, 2 goes to 1. This is 2. Okay. 2 goes to 1, and 1 goes to 0 for shift right. And shift left, serial in comes in. Then Q0 goes to Q1, Q1 goes to Q2, and Q2 goes to Q3. And when it's a parallel load, the data is coming from outside, D3, D2, D1, and D0. And this implements universal shift register. Now, these operations can be changed. It can be in a different order, or it might be having some different operations. These are all possibilities. Okay, so this is one of the applications that we can use D-type flip-flops, synchronized synchronous operations, and we can implement registers. Okay, so if you have any questions, note those down, and you can ask me in the live lecture.